Great. So let's start class. So far, just give a summary. We talk about game theory in general, algorithmic game theory, and we talk about the concept of equilibrium as we talk about several different type of equilibrium: Nash, correlated equilibrium, dominant equilibrium, uh, and some places that how can we solve Nash, like in not necessarily in polynomial time. Then we talk about price of anarchy and price of stability. And one game that I mentioned, these are like the very classic games that actually started the game theory. They got, if I remember correctly, they got also the Gödel Prize because of bringing algorithmic game theory essentially, and the concept of combining computer science and econ. And this happened mainly in like around 2000, the time that there was lots of internet essentially came to life. The same role that AI is playing now, where that time actually internet was playing. And the traffic in the internet, etc., becomes important. That was the thing that the people considered. So we talk about this particular game about non-atomic selfish routing games. And here by non-atomic, we mentioned that these guys that they want to go from point A to B, for example, in this case, these are the pairs that they want to go from S to T, and they can go from the different routes essentially. But if there are too many people are going this is the time that takes for each of them to pass these things, depending on X, how much X is the traffic, that at that time, what will be the traffic time essentially for these people, the time that they do. And we talk about this multi-commodity version of that we have essentially a directed graph. And the people, there are these people who want to go from that they want to go from essentially S1 to T1, and then from S2 to T2, and so on and so forth. The people want to go there, and they try to minimize their time. And we want to see what will happen in equilibrium. We discussed that if you are in equilibrium, because all of these guys, they are going through different paths, but all these paths should have the same waiting time. Otherwise, I mean, the people just in the Nash equilibrium, if everything is the else, is the same, then these guys, they may take a different path. Good. Now we wanted to talk about the price of anarchy. What was the objective that we were talking about? So we talk about the Brazos paradox, but the objective that we talk about was this. This is the objective that we try to essentially optimize. So we said that we try to minimize the total traffic time. What is it? Is that for each path P that they are sending, P is the union of all paths. Actually, the union of all paths, even we have S1, T1, S2, T2, take all the paths that you have, it might be exponential. But as I mentioned, you can always, for each flow, you can decompose it into polynomial. But consider all these paths, take the union of them over all of them. See that how much would be the f of p, how much flow are doing that. This is essentially like if half of the people are using this, then say, okay, this is one half are using it. What would be the traffic for that, the traffic time for this? That would be Cp of f, not Fp. Why? Because you want to see that maybe on this path, there are some other essentially, so this is the path, but what is the total flow that exists on path from all commodities? And then sum it up. And as we discussed previous time, if you remember last time, we said that this actually is equal this by changing the order of essentially just writing the formula and changing the order of two sigmas. Then we could get this one, that go for each edge E, just compute CE f of E. So it means that what is the FE is the total flow that goes through this edge, and there's no cancellation of flow here, times f of E. If for each edge, see how much is the cost, and then this is the total thing that we try to minimize. Good. Now, so we want to say that when we are we want to talk about price of anarchy here. And as we discussed, price of anarchy and price of stability here would be the same. Price of anarchy was the one that essentially considering the worst Nash cost, this essentially, versus the optimum that it just tried to optimize this one. It tried to route these guys. There is no, concept of equilibrium or something. These are like some kind of dumb objects. That's oh, you will go through this path. This is dictatorship. Versus anarchy here, that these are selfish. So price of anarchy, and then price of stability was the price of the best Nash. But here we are saying that there is a unique Nash. When there's a unique Nash, price of anarchy and price of stability would be the same in this game. This is called congestion games, essentially. Good. Or non-atomic selfish routing games. Good. So we try to, as I mentioned in this class, we try to go some of these classic examples, the fundamental thing that they are done, and we talk about also new stuff. But of course, we cannot cover everything. We just try to see the basic stuff. Then, of course, you can read more and use AI to get more information as well. Good. So, so let me just our drawing here. Good. So the first way we want to say that what is the existence and uniqueness. I try to give you some ideas essentially about these ones. And this might be the best motivation is something like along here that I'm talking about. This intuition. So here, this is the main intuition between this. So we want to say that what will happen in the equilibrium, that is anarchy, everyone try to do the best thing and they reach an equilibrium, any equilibrium. Versus the optimum solution, that these are the path, this is the optimization that this is a convex program that actually I can solve. The main intuition is that equilibrium flows and optimum flows are the same things, just with respect to different set of cost functions. Good. So what is the, now let's go to this one. So we want to see what are the cost functions. So let's consider this one. Let's talk about the we talk about the optimum here. Good. So let's GDC star. This is, as I mentioned, this is the cost function that we are doing. This is C for Nash. And this is C star for optimum. And then we relate these two together, see how they are. Let's GDC. The graph is the same, the demands are the same, because we want to send the same demand between each of them, so the demands are the same, the graph is the same. Just the cost function would be different. And we want to say these are the same thing. So let GDC star be a non-atomic selfish routing such that for every edge E, the function CE star is convex and continuously differentiable. Good. So what is the function that we are considering here? This is the one that we are trying to optimize here, is this one. Okay, so we try to minimize this one. Good. Star, whenever we are using a star means optimum essentially. So C star is a convex and continuously differentiable function. Let C star prime, this is essentially the marginal cost function of edge E. What's the meaning of that is that essentially you differentiate the cost function C star on this, the flow that is going. So that is essentially the differentiation that we are doing. Then F star is an optimal flow on this. Again, S star, we mean optimum. If and only if for every edge, every commodity that belongs to 1 to k, commodity means the different pairs that the people want to go there. And every pair pass on this, if the flow on this path is greater than 0, then the marginal cost, means the differentiation on this path P, should be less than or equal to the path P hat or P tilde. Good. So it says that if essentially C star has this one, the function that optimizes this one, good, for any path that any two paths that you are taking, if the flow is greater than 0, then it should be equal. Essentially, that flow greater than 0 means that it is this path belongs to the support of this distribution because of the distribution that are sent. Then that should be less than or equal to the flow of any other path. This is actually very familiar. We have seen similar things, exactly what in the definition of Nash. So why this is correct? This is correct essentially from essentially that comes mainly from the convex optimization, that if it is the case, if you take the margin, because it's the convex things, if there is something like that, then we can of course change the flow from this one. So if you want to have this flow, if you have then some flow here, if really for the path P, the flow is greater than 0, if it should be less than that, because if it is greater than something, then why do you send on path P? Route it on path P hat or P tilde, correct? That have because that is the marginal cost. What's the meaning of marginal cost? The differentiation. It means that you have this path that is going that instead of just sending through this one, if the margin of this guy, marginal cost of this guy is better. So instead of routing through this path P, just send it on the path P tilde. This is exactly the same definition that we had it for Nash equilibrium. So you see, this was exactly the definition that we had for Nash equilibrium. That if you consider essentially any selfish routing game, then for every pair PP hat, PP tilde, then if the cost is greater than 0, this should be, PP should be less than or equal to CP. So what's the meaning of that? So why this theorem is correct? This theorem, the second theorem, this just comes from convex optimization. It's the basic theorem, essentially. As I mentioned, if the marginal cost is less, then it means that this is essentially the way that even solve the convex program. Then you will send it essentially to this one. It's better path. So that comes from this. So what is the meaning of that? So it means that here, note that what is the way to essentially to show that we have a good properties about Nash equilibrium and this is unique, etc., is that we want to relate the Nash equilibrium with this optimization. The issue is that we don't know what is the exact C star here. So the C star here, we don't know what is it. We know that we want to optimize something like this, essentially. We want to minimize the C star, which is some objective function that we try to minimize, but we don't know what is the exact function. But this is very similar to this one. So what do? I will just make this one equal to C P of F star. Good. So this is the marginal cost. I don't know what is the exact meaning of the CP star, but I know that the if you take the differentiation, if the marginal cost, then that should be equal. If I put it equal to Cp of f star, the travel time in the Nash, then I have this property. What's the meaning of that? It means that to get actually the C star, I only need to do the integration to get this. So here, so to define this one, I will define a potential function. So I define a potential function. What is this potential function? It's just going over all edges is C star of. What is the C star of? Instead of this, I can write it. Instead of C star, as I mentioned, I will write it the integration from 0 to f of e, C star prime of y. And instead of that one, I will just put simply what? CE of y. Because they are equal. Now, what is the meaning of that? Now I have this kind of potential function that, in some sense, so what is the meaning of that? So the meaning is that because I put this one, it means that whenever the people are finding a better path in the Nash equilibrium, they are just simply optimizing my objective function. What is the objective function is this function, which is equal to this. So this is called potential function. Potential function is that whenever, so this is one way essentially to say that these people are converges to something. It's that there is some potential function. Potential function is that you are just increasing this potential function. And as far as you know that this potential function has some maximum or some minimum, you know that it should stop at some point. And here, essentially, we show that these two are the same. So whenever the people in the Nash, they optimize their cost in anarchy way, they actually optimizing, they decrease this potential function phi of f. Good. So now, what do we have? Essentially now, because we have this correspondence between that, this is the theorem that we wanted to have. We want to say that let GDC be a non-atomic selfish routing game where C of E is this function, or non-negative, continuous, and non-decreasing function. Then GDC admits at least one equilibrium fellow. If F star, F bar are equilibrium fellows for this, then C of E is equal to this for every edge E. Good. The main property is this one that we want to say. And how can we show that this is an equilibrium, at least one equilibrium fellow? By this way of potential function. Good. Now, by this way of defining the potential function, by this way of defining the potential function. Now, like what are the properties that we had? We know that C is non-negative, continuous, and non-decreasing function. As a result of these things, we know that because it is essentially continuous and non-negative. Let me just good. I think that might be better. Just go with this one. Yeah. So what is the thing that we had? We know that this function CE is non-negative continuous. What was the things that we had it here? we had it that this C star should be convex and continuously differentiable. These are the same property, because when you put this property that should be essentially C should be non-negative and continuous, it means that when you do this integration that we just explained, then this C star becomes convex and continuously differentiable. Yeah. What's the difference between C star? So C star is essentially C star is the way that you get this function. So here, this is the integration of this. So far is by definition. Now, instead of this function, I will just put it CE of y. We can just define this function. Exactly. Because the potential function is the one that we define, actually. So we define it this way. Then because C essentially is so essentially the conditions that we are putting here, non-negative, continuous, non-decreasing function, essentially they become the corresponding things for convex and continuously differentiable. Now, the last one that we know that C star is non-decreasing function, that actually implies that, let me see whether I have mentioned it here. Because it is non-decreasing, as we mentioned here, yeah, so that is like the good. So yeah, what are the two properties? The two properties is this one. Now, because this C is non-decreasing and continuous, it means that each of this function C star, because this function, as I mentioned, this is the CE, because this one is non-decreasing and differentiable, it means that this guy is continuous and convex. Now, then the rest essentially just come from the basic math. You can see that what do we have? We have essentially a set of constraints. We know that also this C is essentially is non-negative. It means that this function C star F, it tries to minimize an objective function on a compact set, compact and continuous. Essentially, it means that it tries to minimize over some surface which is continuous. And because the C is essentially non-negative, you know that it attains a minimum on one of these points in this things. What is the dimension of this? The dimension is set of over all paths. So essentially, this is just some basic math after that, because we just change everything from this CE to C star, and then from this kind of non-decreasing, continuous, and non-negativity, we get essentially this kind of convexity and continuity essentially on this surface. And this surface is the set of all flows that we can send it to that. This is essentially continuous things. If you have a convex things over on these continuous things, and because the marginal value is non-negative, it means that it can attain a minimum at a unique set. This is mainly come from the Weierstrass theorem. We can just search that. So this is like essentially the setting turns from that Nash equilibrium into this kind of convex optimization, and the properties there becomes the corresponding properties there. So we know that this attains, because the continuously differential function and the marginal value, which is C, is non-negative, attain a unique minimum on this set, and it is essentially unique. So because the C is non-decreasing, because the differentiation is non-decreasing and non-negative, then we have this kind of uniqueness. What's that?
C is equal to 0.
Yeah.
Then it's not strictly convex. It's just convex.
It is if C is okay. Yeah, that is a good thing. So if it is the so I think here we are assuming that the C should be greater than 0. I think should be positive essentially. I think yes, you're right. So this should be positive actually, not negative. So this is the better things. I mean, okay. So this is the case. So it see it is the case. If it is non-negative, admits at least one equilibrium. But if it is positive, then attains a unique equilibrium. So if C is just non-negative, if we still have an equilibrium, and here we're just talking about an equilibrium. But if it is positive, then actually for all H's, then actually there is a unique Nash in that case. And then you can see that if it is the case also because it is unique flow for this one, then for each edge, also we should have the same flow essentially. That is also easy to see that. But this is the main thing that it talks about there exists. So this is the general way. This is the general way that we are proving for several of these important games. We are proving that there exists a Nash equilibrium. We define some kinds of potential games, like potential. They call it potential game if there is a potential, such that if these people are trying to reach equilibrium, they are optimizing, which means minimizing or maximizing this function. And then because of this generally then turns out this from, I don't know, continuity here and non-decreasing become convexity or not. It means that here it has some maximum or minimum. It means that we should reach an equilibrium and talks about the equilibrium. That's the general way that we can analyze these games. And for lots of games, if there is this kind, if there are potential games, we can often find a polynomial time algorithm. So we talk about, for example, the zero-sum game for which actually we can obtain polynomial time. I think we can define actually for there also some potential. But in general, potential games are a bit more general because if you can define it, for example, here to obtain it, you only need to just essentially to find an equilibrium, you just optimize this convex optimization over these functions. And then you find the optimum and like unique or non-unique, and then that is corresponding to equilibrium. That's the general way of getting the Nash equilibrium. So that's the reason that these games actually are very important. So that's for this part. Now let's go to the second part that I wanted to also show something interesting about price of anarchy. So here we show that, there's a Nash equilibrium, it's a unique, etc. And if it is unique, the price of anarchy and price of stability are the same. Now let's go and see what about price of anarchy. So let's talk about it. So we want to see how much, like when you reach there, what is the total traffic time versus the optimum traffic time? The optimum, we just try to optimize this, but I want to say how big this one corresponds. The first thing that we want to say is this lemma. The proof actually is not hard. What does it say? It says that the inner product. So these are two vectors. C is a vector. This is for f of equilibrium. Correct? F of equilibrium, consider the f that the flow that is in the equilibrium relation. And f is any flow. Good. We always have this one. The inner product of this should be greater, less than or equal to 0. What is the inner product? You just multiply each of these terms together. Good. Now, let's write it there. So say it is not the case, then we expand it. So if you expand it, it would be like this. So you will say that this times this should be greater than this times this, correct? This should be the case. This is just essentially proof by contradiction. If it is the case, Then we can expand this one. So this is like this one. Instead of writing this, we can write it over every path P. Here, actually, that should be f of P. Good. So what is the meaning of that? So say that this flow, for this flow, this the total cost, when you do it by F equilibrium versus another F, this is large. So this, note that this is some of the flows that are sending, and these are corresponding flows. Both of them are feasible flows. So it means that now this flow that you are writing it, you can write it, as I mentioned, each flow, you can decompose it into lots of paths. You can actually send to paths of very equal value. So what's the meaning of that? So if you have essentially S and T, you can just decompose this S and T, both of them. These are S and T, this is the same thing. Maybe actually I can just do it with the different color. So this is the flow. Essentially, this is F EQ. And what is the corresponding things here? Here, this is F. Okay, so the question is that why I have drew 4 paths here and 4 paths here. I mean, it's not the case that there be 5 here, 4 here. Actually, you can decompose both of them into the same epsilon. So because this S and T, when you have it, you can, the flow FQ, and this is F. Both F and FQ, you can decompose it into paths that are size carry only epsilon fraction of the flow and the same epsilon over F and FQ. Good. And this may route it differently. Of course, some of these paths, like maybe this path and this path, might be the same, no problem. But the important thing is that both of these, this guy and this guy, both of them are each path here and each path here carrying the same flow epsilon. That is essentially by this regular max flow min cut type of thing and flow decomposition, we can do that. Now, how can we? Now, if it is the case, if this flow is like that, then we can just simply match any flow here with any flow here. So these two are matching, these two are matched. Why can I match it? Because both of them are carrying the same flow epsilon. And I know that they are satisfying the same demand. So the total of epsilons here and the total of epsilons in F and F of equilibrium should be the same. So I will just do this kind of matching between this flow and this flow. Now, this one is the sum over the F of P. This is just, I think this I should just, yeah, so this is actually was correct. So this is like my mistake. So let me just erase this one. Yeah. So this indeed was correct. Yes. So now, because I know that this sum is greater than this sum, and now I can decompose this flows into these small flows and say each path P is the one that carries only epsilon. Good. It means that at least one of these guys, for one of these paths P, I should have this property. Good. Because I have just a matching. I sum over all these P's that are the corresponding P's there. So the sum here is greater than the sum here. So if the sum is greater than this, it means that at least for one flow path P, I should have this one is greater than the corresponding flow path P in the other. It's the same function essentially here. So it should be for, I can say essentially for this flow path P. Actually, I think this should be this and this. for the p hat. So what's the meaning of that? It means that at least for one of this flow that I'm sending it, for one path p, because both of them are carrying the same thing, one of them should have the same flow. So the flow is the same, the costs are the same, but the flow paths essentially are different. For one of them, at least I should have the cost under f of equilibrium should be greater than the cost under f. So that cannot be the case, because otherwise, then why do I use the path p? Just send it through path p hat in there. And essentially, you can decompose that and you can get this. Good. So I have this thing essentially that comes from the flow. You can, just try to write it more carefully if you want. But now from this equation, now I can get essentially the things that I want. How do I get it there? So let's, this might be the best. By the way, so this is also this one that I have talked about it. It is in the algorithmic game theory book, for example, on page, this is the paper, the book by Papadimitriou, Vazirani, Rock Garden, Hardosh, and I think Christos, that this algorithmic game theory is one of the references for this book, just the algorithmic game theory book. On page 470, it talks about all of this convexity, etc. You can just go and read it more carefully. But I think by now, even if you ask AI, probably that also can give it, especially Gemini gives very clean things for that. So you can read more about this. Okay, now. Good. So let's see, I want to say that the price of anarchy good. Okay. So let's consider the cost function on each edge. These are called essentially affine functions. C of m, some linear functions. C of x is equal to ce times x plus b, correct? This is just a simple. You can actually prove this one for polynomials of larger than like just linear, like quadratic or other thing. But say for now this. Here, their C of E is non-negative and B of E are both non-negative. This is the cost essentially that we have it. And this is for all edges. This is actually considered affine cost functions. So edge, what is the traffic? So for each edge E, how much is if there are flow of X in it, C of X times B of E is H. And this was the case for both Brass's paradox and Pico's example. Okay, so that is the thing. Now I want to say that price of anarchy here would be 4/3. If this instead of x was x to the 3 or x to the 4, etc., then this 4/3 becomes worse, but it still is constant. Let's see how can we prove it. So let's consider F be the optimal social flow. What is F? F is the one that tries to optimize. So this is the optimization function. It sends these flows and tries to do this. But here is the one that we reach to an equilibrium that has this problem. I just write it down. So I know that what is the cost of, FQ, the equilibrium? It is the just sum over all edge E, f of E times f of E. This is because of this equation that we explained previously. So I just write for each E, what is the f of Q times f of Q. Now, from that inner product that I have just mentioned, I know that this is at most over all edge E, C, f of E for any arbitrary f E. Good. So this is the equilibrium. This one is any flow. Why do I have it? Because of this equation. Just because. That was the same thing that we just. Good. So I have this equation. So it is this one. Now, what do I write here? Then I will just essentially adding to this I will just adding and subtracting this sum. What is this sum? So I just add this, and then do minus this. Good. So why do I want to do that? I want to change, because this is C of f of q. I want to change it to C E of f of e, because this is the optimum. Here, when I talk about f of e, indeed f of e is the optimum, correct? F is the optimum solution. So first I have written this one. I have used that lemma to change f of e, f of q, f of equilibrium to f of e. But still the cost function is in terms of f e of eq. I need to change that. How can I change it? I will just add this term over all edges. I will just add this term c of e, f of e, and then I will do over all edges, just do the minus. Good. So this is the optimum. Good. So I know that this is the equilibrium. So I want to say that, what do I want to show? I want to say equilibrium cost is at most 4/3 of optimum. Correct? So this part is optimum. If I show this one, this part, if I show this part, so I have just, so far I didn't do any magic, just plus and minus. If I show this part, CE f of EQ, so what is the difference? They have both f of E, but one is according to the f of EQ, the other one is according to f of E. If I show that this one is at most, this sum is at most 1/4 of C of FEQ, then I'm done. Correct? Because if I show this sum and this is at most 1/4 of this, then I know that this is, then I can write this one. So this is equal to this. This would be, then it would be equal to, I can write it like this. I can write it. This is less than opt plus 1/4 of Nash. And this was Nash, correct? Equilibrium was Nash. So then out of this, Nash is less than opt plus 1/4 of Nash. It means that 3/4 of Nash is less than or equal to opt, correct? And then it means that Nash cost is at most 4/3 opt. And I'm done. Good. Just some simple equation. So the only thing I need to compare this one with this one. Essentially, I need to compare this one with this one, essentially, with this equation. Good. So if I can bound this one, I say that it is at most 1/4 of Nash, I am done. Good. Now, where should I care about this cost? Because this is some additive cost. If I can just bound this one, then as I mentioned, I can just write this one, and this Nash is at most opt plus this one, then I get these equations out of it, just bring this one the other side, and then I get Nash 4/3 opt. And this is the, if you remember, that 4/3 actually is the one that we talked, for example, in Brass's paradox, we talk about that when you add one edge, it can become 4/3 because that was all linear. And also note that there, we said that the optimum does not decrease, does not increase. So that was the reason that we discussed that if I prove this one, it shows that if I add one edge or any number of edges, essentially, the price of anarchy cannot become more than 4/3. But anyhow, this is it. So that's all equation. So the only thing I need to just compare this one, this cost. Let me just erase everything. I only need to compare this cost plus this cost. Now, one thing is that I only care about the case that I only care about this equation when f of EQ, because, okay, so C of E is non-decreasing, correct? So I only care about the case that f of EQ is greater than f of E. Because in that case, these terms become greater than this term. I have some positive term that I'm adding here. Otherwise, I'm adding some negative term. Negative terms only helps me. It says that opt is less than some optimum plus some negative term. Essentially, it means that Nash was better than opt. Good. So the part that hurts me is the case that essentially this part, f of EQ is greater than f of P. I want to bound on that case. Okay, so this is actually, I think this was not the original thing this was a thing that Timur Garden and Eva Tardosh had the paper. This is not the original proof, but this is a much nicer proof, essentially, that there are some issues also in that paper. But anyhow, this is the one that we are talking is by this set of people. This is a very nice geometric proof that why do we have this equation. Good. So what do I want to show? Let me just good. Now let's see why do we have this property. So this is the geometric proof that we have. So what do I want to show? I want to show that for any f of E in these equations. So I can just consider E. No, instead of proving this one for the whole sum, I will just want to prove for each equation individually. What do I want to show? I want to show that I want to show this one is, so let me just write it down here. So what do I want to show? I want to show this one, that this is less than or equal to 1/4 of what? Sigma of E C E F E. Actually, this F of equilibrium times F E of equilibrium. Good. So I want to just show this. To show this one, I want to say only I will focus on edges that f of EQ is greater than f of E, because the others are negative term, doesn't matter. So I only need to show this one, that C of E, f of E, EQ is minus C of E, f of E. This is less than 1/4 CE FE EQ times f of e. Good. I only need to show for whenever f e of eq is greater than f of e. Actually, this I need to times f of e. So instead of proving the whole sum, I will just say individual ones. For those that are negative, I don't need to do anything. Only for positive guys, I need to do that. Positive means f of eq is greater than this. Because if this is the case, because c is non-decreasing, also means this is greater than this, that's a positive term that I have it. For the, I need to calculate essentially for a consider positive term. Okay, now I show the whole things by just some geometric things. How do I show this one? Let's go this one, see which one is better. So the type one is nicer generally, but some of them is written by a student. There might be some typos, mistakes, etc. That's the thing that sometimes this would be better. Okay. Let's actually go here. That might be. Let me see which one is better. Yeah, this one. So here I wanted to show this one or this. But let me just write it down, make it sure it is correct. So here I have also, I need to, this is the thing that it should have written is this. So this is f of e times of e times f of e of equal. This is the one that I want to show. Good. Just see this diagram. What is this term? So I have just drawn these things. I know that f of this is by definition, because as I mentioned, I only care about the case that feq is greater than f. Good. So then what is this one? So this is the, and I know that because of this c, because also c is non-decreasing, this should be less than this. Good. Now this area, this is a very nice geometry. This is the area of this triangle. Correct? Because this is f of e here. This is f of e times this minus f of e times this. What is c of e f of eq? That is the area of, this is the whole, this. I need to say that essentially, that red I need to say blue less than equal to 1/4 of in terms of area. Good. And note that we have this property, b is greater than 0. I have this assumption that b should be greater than 0. And c was also greater than or equal to 0 because I had it non-decreasing. So it means that c cannot be negative. So that's the reason that I have this check. Now, then this is actually, if you want to see geometrically, is very easy. Why? Because you can show that. I mean, easily see that. Now, let me do just another color here as well. So the screen. So I can just consider this a square and just divide it into this. I know that this is less than or equal. These two are equal, and these two are equal. Okay, so we don't. So I think in terms of the area, yeah. So this is. I mean, if these are exactly equal in the middle, we have it. But anyhow, you can show that. Okay. So what is this? This is actually easier. That this one, you can show. I will show this. This essentially this square. This rectangle. The area of this is essentially at most half of this triangle. And the area of this triangle is half of this whole rectangle, big triangle. So I say that the blue, what is this? This blue rectangle, the area is at most half of this triangle, the green triangle, and the green triangle is at most half of the red rectangle. So I will get this 1/4 and done. Now, if you want to show that essentially why do I have this one, you can actually this part that high. Yeah, of course, if these are equal, then you have this case. So if this is exactly is the middle and this is exactly in the middle, then as I mentioned, these two are equal, these two are equal, and you get this one is half of this. But it might be not equal. So let's see how can we show always. So I want to say equal actually is the somehow the worst case. Like this is the case that is exactly half of it. All other cases would be actually less than half. How can I show that? This is I just write a simple equation. So I will say this is x. So essentially this is like, so if you consider this part, give me 1 second to just make sure that this is. So yeah, so this is, so let's see this is x. So I just want to show that essentially the only thing that I want to show is that this is at most half of this triangle. Good. So let's say this part is x. Say this is 1, the total. The rest is 1 minus x for some x. Good. So what do I have? So if this is x, and say this is a and this is b, what is the area of this triangle would be half of a times b, correct? That's for triangle. Now let's see for rectangle. So that is for triangle. Now what about for rectangle? So there, because this is x out of essentially 1, it would be x times b times 1 minus x times a. Good, I'm just using simple geometry. So it would be x times b would be this one, and then 1 minus x times a would be this one. This would be the area of this. Now you can see that this x times 1 minus x, the worst case happens that when x is equal to 1/2. Good. In that case, this triangle would be exactly 1/4. The same thing that we mentioned. If it is the case, for example, if you consider x is equal to 1/3, see what will happen. And then 1 minus x becomes 2/3. Then in that case, you can say that I will get it 1/3 b times 2/3 a, which becomes 2/9 ab. Correct? Here, which is less than this, which is less than 1/4. So the worst thing, essentially, that's the formal proof, essentially, now that this is I just write. This was the case. So this is the I can just write essentially these equations. This would be the area of this guy. This I have x 1 minus x, and then the worst case will happen when x is equal to 1/2. Exactly when it is the middle. So this area is 1/2 of this, and of course this triangle, because b is greater than 0, would be at most half of this rectangle, and this rectangle is exactly this one that we again the one that we had it is f of e, and this has the f of e. Good. So that's the result. So this is, but here we have proved essentially for this function, correct? As I mentioned, if this is x to the 2 or other functions that people have considered it for more general function, you can still, there are some geometric version of it. Actually, you can see this would be a good read. This is a very nice paper. I think this paper that they have it. Yeah, so you can read more about it in this book. And this result is the result, I think, did I mention this here? Yeah, these geometric results, I mean, you can find the reference from there, but this is Nicholas Ster, Cora, and there was a third author for this paper that you can find it. I think you can find it in there, these references. Nicholas Ster, Jose Cora, and third, they were actually both at MIT at the same time. This was a professor who was at that time at MIT. Andreas Schulz. So this is the Nicholas Ster. I just write the last names. Ster is that Meta now. Cora was a Cora. He's in Chile, and Andreas Schulz. So Andreas was actually professor at MIT, and he was the advisor of both of them. That's a very nice, clean proof for this one. The original proof was, I mean, it had some messy, and I think, if I remember, it had some bugs as well. But this is a very clean proof that shows these things. And that works even for more general C. So there is no need to consider, even if any polynomial, you can get some bounds, and there are some interpretations of that you can read. So this is for this function that we were talking about. But as I mentioned, it can be any polynomial. I think the people consider more general. So that's a very nice one, very cute proof, essentially, that shows that this is, and this is important. This is one of the non-trivial price of anarchy. As I mentioned, this original paper of Kim Garden and Eva Tardosh, that actually got a Gödel Prize because of this, because it's one of the early things that they could get a very nice result about price of anarchy and bound it and connect it essentially with convex optimization and get some non-trivial results. And this 430 is the worst case, etc. And good. So I think that is like a good example for this price of anarchy things. We are talking more about equilibriums in the future, as well as some other important topics essentially in game theory. But equilibrium is the important things that we will cover further.